Do you tape all of your lessons?
I don't tape every lesson. For instance, I don't tape the recitations. But I'm taping the lectures. I'm trying to. Yeah. Okay, so actually,
I mean, for all your classes.
I try to, yeah. I find it gives my mother something to watch. All right.
Did
So,
she give you feedback?
Does my mom give me feedback? Not mathematical.
Like you should never wear that shirt with that tie again type of feedback.
I have gotten that feedback, yes. But I get my students to help me with that too. For instance, you all remember the Target affair. I have an outfit that my wife and I both thought was a very nice outfit. For years I've been wearing it, and then they told me, "Boy, you look like an employee at Target." It's a red top with the khaki pants. Now it's really hard for me to wear that anymore. All right. So, well, yesterday we wrote down the polar form of a complex number. That was this thing that looked like z equals r e to the I theta. And I want to talk a little bit today about the geometry of complex numbers, which this polar form is going to make much easier. Now, there's a lot to say about the geometry of complex numbers, and I'm only going to say a very, very tiny part of it. But it'll be good enough for what we need. And then the second thing that I want to talk about is very much related to the first part, which is a formula called de Moivre's formula. And this is really nothing too major after what we've already done. But it's worthwhile and is given a name. Okay, so let's just quickly recap. So, if you start with a complex number, which we could write in the form z equals a plus bi, this is the so-called analog of rectangular coordinates. Right? If you try to graph this, right, well, this is your real axis and this is your imaginary axis. And you just go A units on the real axis and B units on the imaginary axis and plug this point. And the way you label this point in the, well, if this was R2, right, the Euclidean plane, you would write this as A comma B. But since this is the complex plane, you denote this by, well, A plus BI. And of course, we can draw this vector going from the origin to that point A plus BI. And this vector has a magnitude. So the length of this was the square root of A squared plus B squared, which we get by the Pythagorean theorem, for instance. And so, well, if we remember that A plus BI is our point Z, then we wrote this distance as the norm of Z, right, or the magnitude of Z. All right. Then we also notice that once you know the magnitude of this vector, then this point is also determined by, well, you take the magnitude and then you look at the angle that this line segment makes with the positive x-axis. If you know this angle and you know how far out you have to go, that also completely determines this point. And that gave us a different way of representing the point. And well, then we notice that if you actually took, say, this over here to be the unit circle, so this is length 1, then this point right there corresponds to the complex number e to the I theta. And so if you want to go out to this point over here, well, all you have to do is multiply by the magnitude of z. And that'll give you the point out here. And so this point here in polar form is the magnitude of z times e to the I theta. So in general, we can write this z in two different ways. And you can just use trigonometry to work back and forth between these, up to one little detail, which is that, well, this theta is actually not unique. Right? You have infinitely many choices. Right? You can get all the different thetas by adding 2 pi's up here. Right? Replace theta by theta plus 2 pi, or theta plus 4 pi, or theta plus 6 pi, or theta plus 8 pi, or you can subtract 2 pi's. Right? That always just takes you around the circle. Okay, so how to use the trigonometry? Well, we already know how to get from, say, a and b to the norm of z, right? Just use this formula. And, well, how do you get the angle? Right, well, yesterday we saw that, okay, well, if you know a and you know b, right, b is the height, a is the width of this triangle, and so you can just take the arctan of b over a. Right, so theta could be the arctangent of b over a. At least this is one possible theta. Now, we're going to, well, let's write it down now. All right, we're going to immediately come up with a convention to deal with this problem of there being too many thetas. So, if we write z is equal to, well, let me just write r here instead of norm of z, but it means the same thing, right? It's just the length of this vector from the origin to z. If I have z equals r e to the I theta, this is also the same as r e to the I theta plus 2k pi, right? Where k here is any integer. Okay. Just any multiple of 2 pi will work. Okay, fine. So which theta should we default to? That's the question. I mean, if somebody says, I have a z, it's a plus bi, can you give it to me in polar form? Well, you can use any one of these, right? There's infinitely many of them. Is there one that we can agree to default to? And the one that we agree to default to is the one between, well, in radians, minus pi and pi. Okay. So the angle could be anywhere in here. That, just as if you didn't go around. We're gonna, the one we agree upon is the one where you don't have to go around more than once. And in fact, what you do is you go up and you stop here. Okay, so we'll take all the ones from 0 to pi, but we're never going to go past pi. If there's something that was going to go past pi, an angle here, we'd prefer to go backwards. Okay, so we're going to go, so, by the way, so we're going to give a name here. This theta is called the argument of z. And by convention, we can define arg of z. Hello. We can define arg of z in the interval minus pi to pi. And now let me see which way I want to. Yeah, I think I'm going to not include the endpoint on the left. Right, pi and minus pi are actually the same, giving you the same point over here, so you have to choose which one you include. Okay. All right, so let's just do a quick example. Let's say I let z equal, well, easy one, 1 plus I. Okay, and I want to write this in polar form. Right. Z in polar form. Well, we need two things. We need to know the r, and we need to know the theta, right? Or if you like, the argument. Okay, so what's r? Well, r is the magnitude. Right? That's how we always get it. So this r is the same as this magnitude of z. So what's the magnitude of 1 plus I?
2. No. Radical 2.
Radical 2. How do you get that, right? Well, it's square root of 1 squared plus 1 squared. So square root of 2. Okay. Let's draw a quick picture. Okay, so 1 and 1, right? There's your I-axis. There's your real axis. So I draw 1 plus I. Of course, this is just if you did this as a triangle with side length 1 and 1, so of course the hypotenuse is root 2. So z equals root 2 times e to the I. Well, now we need the argument. So the argument is this angle here. So what does that angle have to be?
Pi over 4.
Yeah, exactly. It's an isosceles triangle, right? And it's an isosceles right triangle. Well, there's only one way to do that, up to the length of the side, and that's to have a 45, 45, 90 right triangle. Okay, so this angle has to be pi over 4. If you like, right, theta is the arctan of 1 over 1. Because the arc is supposed to be arctan of b over a. Well, b over a, both b and a are 1, so it's just 1 over 1. And then you say, okay, fine, what's the arctan of 1? Well, remember, tangent was sine over cosine, and you say, okay, what angle gives you the same sign as cosine? Well, it's pi over 4. So and then this z is root 2 e to the I pi over 4. Now, if I went the other direction, down here, say these are now minus 1, minus 1, right? So this is minus 1 minus I. Okay, it's a bad picture because it looks longer, but pictures are misleading. So if now z is minus 1 minus I, then in polar form, z is, well, what's the length of this?
Still radical 2.
Still radical 2, right? The minus 1 and the minus, I mean, the minuses are irrelevant as far as calculating the magnitude. So we still get a root 2. It's still going to be e to the I, but now, what's the angle? Right. Well, we could go this way all around, right? You know, okay, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. But 5 pi over 4 is greater than pi. And by convention, we don't take the ones that are bigger than pi. Right? If it goes bigger than pi, we go backwards. So we'd go minus pi over 4, minus 2 pi over 4, minus 3 pi over 4. So that would be e to the minus I 3 pi over 4. So we actually end up using this angle. It's just a convention. You can choose different intervals to take. Fine. But this is the one that we like to use. Okay. So this is all going to be important stuff for us. All right. So let me give you a very quick application of the polar form that makes things look a lot nicer than the rectangular form, to maybe indicate why we like to use it. Well, we already saw one, which was finding roots of unity yesterday. It was actually very easy to find roots of unity. Let's see another one. Recall, we know how to multiply two complex numbers. Okay, you have to FOIL this out. You get AC, and then, well, these two things are going to give you another real part, because the i's will become a minus 1, so you get minus BD. Okay, that was the real part. And then you have an AD and a BC, that's your imaginary part. Okay, that doesn't look really pretty, and it's certainly not intuitive what's going on. And if I gave you a picture of two complex numbers in the plane, and I said, okay, now show me where the product of those two is going to be, what chance do you have? Right? Let me draw that picture. Okay, I'll put one over here, right? There's your A plus BI. I'll put another one over here. There's C plus DI. What does the product of these two look like? Where is it going to be? I mean, it's not so... I mean, well, okay, it's going to be there, but I don't really have a good intuition for where those points are. All right? Okay, fine. Let's do it again, but in polar form. Start with a vector here, and instead of giving you the A plus BI, let me tell you that it's R1 e to the I theta 1. Why do I use a 1? Well, because there's going to be two of these, right? So take the labels. Okay, and then this one is R2 e to the I theta 2. Okay, what's the product going to be? Well, I have to multiply R1 e to the I theta 1 times R2 e to the I theta 2. But this is not so bad. You just got these nice real numbers at the front. Okay, so, okay, that's easy enough. R1 times R2. And then I have e to the I theta 1, e to the I theta 2. Well, what can I do with these last two? And where is it, right? What's the angle? You just add the angles. Right? So here's theta 1, there's theta 2. If you add the angles, well, you're going to get somewhere like there. Right? There's theta 1 plus theta 2. Right? And then the length, well, I have to multiply R1 and R2, so this might have to go out quite a bit. Who knows? Depends on how big R1 and R2 are. And so this then would be R1, R2, e to the I, theta 1 plus theta 2. That's a much easier way to multiply it, I think, right? Okay, so this is part of what I'm talking about when I say the geometry of complex numbers. This is one part of the story. This is not so bad, right? And this is going to be relevant at the end of the day when we talk about Moivre's formula. Any questions? Okay, let's do a little more picture understanding. So, what if I have a vector, and let's go back to regular rectangular-like coordinates. I have A plus BI, and I have another one which is C plus DI. Now, if I want to add two complex numbers, this is very easy, right? You just add the real parts and add the imaginary parts.
Like vector addition.
It's exactly vector addition. It's exactly vector addition. So, to draw that, what happens, right? Well, you just effectively, you add this real part up here, but then you also are adding the y part. So basically, you take this vector and put a copy up here that ends at this point. Just put a copy up there. And it should be, if these lines extended on to infinity, these would be parallel. Okay, and when I do that,
Parallelogram.
yeah, exactly, right?
In physics? Oh, I took physics like 3 years ago.
And so what I get, if I draw the diagonal of this parallelogram, I'm getting exactly the vector that corresponds to a plus c plus b plus di.
doing the reciprocal.
Oh, yeah.
Because then. the
Yeah,
rule
because we
follows.
did that
the other day. That's right. Okay.
Alright, so this part isn't so, this is not going to be so earth-shaking. It's quite nice. Well, so I want to know if I should state this. I think I just state this for, yeah, just for natural numbers. So let's say I want to, let's say I want to take a complex number z and raise it to the nth power. And for now, n is just a natural number. Well, I know that I can write z as its magnitude times e to the I theta, where here theta is the argument of z.
How do you say that name?
Is that a W?
Moivre. This, oh, sorry, this is, that's a V and that's an R. I kind of got,
Okay. He was French.
yeah.
Mm-hmm.
Moivre. Yeah.
So easy to tell.
I know.
So we can write our z to the n in this way by just converting to polar form. And then of course it's very easy to do this, right? You just put the n in. So you get the magnitude of z to the n, and then e to the I theta n. But then yesterday we saw that, well, e to the I theta is cis theta, right? Cosine theta plus I sine theta. So you can actually write this as the norm of z to the n times cosine of n theta plus I sine of n theta. So this is Moivre's theorem. So if you want to exponentiate a complex number, you can actually, as long as you know the argument and the magnitude, right, you can just write it down explicitly like this. And what's nice is, well, this is just a real number over here, so raising it to the nth power is no big deal. Over here, you've turned exponentiation, which normally is harder, into multiplication. You're not looking at cosine of theta to the n and sine of theta to the n, which might be harder. You're actually reducing it to cosine of n theta, which might be easier. And when we start next time, I'm going to show you a really cool application of this that allows you to write down formulas for things like cosine of n theta. This is just a real question, right? You already know, for instance, that the cosine of 2 theta is cosine squared theta minus sine squared theta. And you know that sine of 2 theta equals 2 sine theta cosine theta. We're going to use this formula to actually come up with formulas for sine of 3 theta, sine of 4 theta, cosine of 3 theta, cosine of 4 theta in a really easy way, just using de Moivre's formula. So that's how we'll start next time. Okay, I'll see you tomorrow.